Good afternoon. We are going to be doing something different from what we did previously this afternoon. I remain Edward Wasurum. We are going to be doing assumptions of classical ordinary linear stochastic regressions, or what is also known as the OLX assumptions. There are many assumptions of the OLX. In some textbooks you can find 11 of it, while in some textbooks you can find 9 of it. But today I want to inform you that we have 11 assumptions of the OLX, but 8 of these assumptions are of the stochastic nature. But today we are going to be looking at 9 of these assumptions critically. These assumptions are like set down rules and regulations that guides all econometric studies. Recall in my first study I told you that we have two types of econometrics. We have the theoretical econometrics and we also have the applied econometrics. And both theoretical econometrics and the applied econometrics makes use of two assumptions. The assumptions are of the classical least square or of the Bayesian assumptions. But for the sake of this class, our emphasis will be on classical least square assumptions. So the first assumption of the classical least square regression is linearity. And this word, linearity, is not a new word to all of us. This word is something that we have been hearing over time. And when you hear the word linearity, it sounds something that looks like a straight thing, or something that is certain or moves in a particular trend. If something is linear, it has a particular movement or shade at which they work, or it works, or it moves over time. So in regression analysis, it is expected that the dependent variable, which is the variable at the left hand side, can be calculated as a linear function of a set of independent variables plus a disturbance terms. Recall in our last video I told you that all variables in the left hand side are called the dependent variable, while the ones at the right hand side, they are called the independent variables. So the first assumption of the classical least square is that 1. The variable at the right hand side must normalize the variable at the left hand side, which means that the independent variable, which is the variable at the right hand side, is critical to the functionality of the variable at the left hand side. If you use a man and a married woman as an example, the head of the house, the man, is the dependent variable, while the woman is the independent variable. If the man is married to one wife, it then means that the man is dependent on the woman, which is independent variable. But if the man has more than one wife, it then means that the man, the dependent variable, depends on the independent variables, which are the wives. So the first thing is that the independent variables must explain the dependent variable. That is what the term linearity means. If something is a linear function of a thing, it then means that the particular independent variable must explain the dependent variable in a straight form without being interrupted. So that is the first assumption of the OLX. And another caveat in that assumption is that there is always a disturbance term. Recall that in econometrics we are dealing with inexact condition. Inexact in the sense that we always assume that all things are equal, but we know that everything are not equal. So in economics, we believe that there is always a UT that is added to our equations. That UT captures the unforeseen observations or information that the researcher was unable to incorporate. So while you are looking at linearity, there is always a plus of the error term or the idiosyncratic element. The second assumption is that ST has some variability, and this implies that the value of ST are not the same in all observations. If I still use the example I used before, example of a man and two wives, for instance, or a man and a woman, it then means that the value of the wives are not the same over time. The wives came with different characteristics. The wives exhibit different qualities. So there is variability in STs. That means that STs do not have the same quality at all times. So that is the second assumption of the classical least square, that the STs, that the explanatory variables, do not have the same quality, do not have the same characteristics. There is variability over time. Then the next quality of, or the next assumption of the classical least square is that the ST is non-stochastic and fixed in repeated samples. Okay, when I treated the unit truth text, or when I treated the time series studies, I told you that time series studies are stochastic. They have stochastic characteristics. And I also told you that when something is having a stochastic characteristics, such a variable is unstable over time. But in this assumption, assumption 3 is telling us that the value of the explanatory variables are non-stochastic and fixed in repeated sample. That means that the values of the x's, the value of the variables at the right hand side, which in assumption 1 will say that the x has some variability. If they have some variability, they are not the same. Then the non-stochastic nature of this particular variables that has some variability implies that in their private characteristics or their individual characteristics, they do not change over time. That means that their individual characteristics are fixed in repeated sample. That the same way a particular lady will behave today, in the same way she will behave tomorrow, in the same way she will behave next tomorrow. That means that their characters will not change. Their characters remain the same over time. That is the meaning of non-stochastic in nature. If something is stochastic, it changes. If something is non-stochastic, it doesn't change. So the non-stochastic nature of the S implies that the repeated character of this particular STs, that the explanatory variables, do not change. The value of the character of ST today is the character of ST in a different observation. If you use ST in different observation over time, the ST will give you the same quality, the same behavior over time. So that is what this particular assumption 3 is trying to explain to us. Then assumption 4 of the classical least square states that the expected value of the error term is 0. This means that the disturbance is a genuine one, and this implies that the error term that is being used in the study will always sum to 0. The larger the sample size, the more the disturbance term tends towards 0. And this confirms the law of large number that we were able to discuss in our preliminary classes, wherein I told you that the larger the number of observations, the better the robustness of the model, because larger observations give model better fits. So it is expected that the error term will have a mean value of 0 in every good econometric estimation. And recall that the error term is always explained with the subscript UT. Then assumption 4, the homoskedasticity assumption. These assumptions require all the disturbance terms to have equal variances. That is homoskedasticity. This implies that UT, this implies that the variance of UT is constant. This implies that the variance of UT is what? Constant. So the word homoskedasticity, let's look at it and actually dig into the meaning of the word homoskedasticity. Okay, homoskedasticity as used in econometrics is the opposite of heteroskedasticity. Homoskedasticity occurs when variables have the same variances, when variables have the same errors, when variables have the same opportunity, also when variables have the same opportunity to be bad over time. When variables are exposed to the same characteristics or circumstances, we say that those variables are homoskedastic. Or we say that there is homoskedasticity in the distribution of a particular score. But when there is heteroskedasticity, we now mean that there is unequal distribution of variance or errors in the model. So basically it is expected that the value of UT will be homoskedastic. That means that the error construct in the econometric estimation will be the same in all estimation. That is what that particular fifth assumption is telling us. Then assumption 6, serial independence. Assumption 6, serial independence. This implies that all the disturbance terms are serially independently distributed, or that they are not correlated with one another. Serial independence. The error construct in the first model is independent of the error construct of the second model. So all estimated econometric model will have different disturbance term. That is the meaning of that particular assumption 6. Assumption 7 has to do with the normality of the residual. Assumption 7 has to do with normality of the residual. The disturbance term in all models are independently identically normally distributed with the means of 0 and a constant variance. Actually, in all econometric estimation, we always have what they call the residual, which is the error term. And for the residual to be normal, it will be in line with the Gaussian condition. And the Gaussian condition is built on normal distribution of variances. So normality of the residual in the context of the assumption of the classical least square implies that the error term will have a mean value of 0 and also have a constant variance. So critically, that is what that means. Then the eighth assumption is that n will be greater than 2. N as used in this assumption is the number of observations. N as used in this econometric assumption means the number of observations, the number of years the researcher intends to actually conduct his or her research. That is the N. And when N is more than 2, it then means that you are saying that it will be more than 2 years observations. And once N is more than 2, it then means that the explanatory variable will well explain the explained variables. So the ninth assumption is what we call the multicollinearity assumption. Multicollinearity assumption is the ninth assumption of the classical least square. And this assumption states that there are no exact linear association amongst the variables. And whenever time this assumption is violated, it means there is a presence of multicollinearity. But basically, to ascertain the presence or absence of multicollinearity, we actually look at how the explanatory variables behave or interact among themselves. So as we progress further, when we are going to be doing post-estimation tests or violations of the classical least square, we are going to perform correlation matrices using the explanatory variables alone to actually check the presence or absence of multicollinearity. So these are the 9 assumptions of the classical least square that we are going to be dwelling on in this study. And thank you for staying tuned to this page. In our next class, we are going to do something more serious than this. Thank you and God bless you.